Hello everyone, we are continuing the Unit 6 Special Purpose Machines to cover the remaining topics. In the lecture 1 we have covered the construction, working principle, characteristics and applications of induction generator and linear induction motor. Now in this lecture we are going to cover the synchronous induction motor and permanent magnet synchronous motors. So after completing the synchronous induction motor and permanent magnet synchronous motors, we will be able to describe the working principle, rotor connections and performance characteristics of synchronous induction motor, and also we will be able to explain the construction and working principle of permanent magnet synchronous motor, that is PMSM. So first we will see the probable questions that may be asked. So why the synchronous induction motor is provided with relatively large air gap? Then next is why the synchronous induction motor is provided with heavy rotor windings. Why the synchronous induction motor is provided with few field turns and low excitation voltage. Describe the construction and working of a synchronous induction motor. Explain the principle of operation of permanent magnet synchronous motor and how can the motor be made self-starting. So these are few questions that may be asked, but there may be more questions, right? Now first we'll see the synchronous induction motor. Introduction. The synchronous induction motor, as its name implies, is a machine which is capable of running both as an induction motor and as a synchronous motor. So during starting it will act as an induction motor, and during the normal running condition it will act as a synchronous motor, right? So due to its mode of operation during starting and due to its mode of operation during normal running condition, that will be as a synchronous motor, right? So during starting its mode of operation will be as an induction motor. Now construction. The secondary winding of a synchronous induction motor consists of a polyphase winding, right, and that is a three-phase type, and the rotor is uniformly slotted around the whole periphery. There is no saliency. That is what? It is a round rotor machine. Means what? Non-salient or cylindrical type rotor machine. The secondary winding is what? It is a rotor. Stator is same as that of a three-phase induction motor. Now the working principle. For the synchronous mode of operation, it is necessary to supply the rotor winding with direct current, that as we have seen in alternator. In the same way that for the synchronous mode of operation of the synchronous induction motor, it is necessary to supply the rotor winding with direct current. So when the rotor winding of wound rotor induction motor are excited by a direct current, the MMF distribution develops alternate north and south poles in the same way as it develops when a three-phase current flows, right? But the essential difference is that the DC excitation being fixed, the pole axis due to the DC excitation are fixed in space and do not shift as in case when the rotor winding carries AC. Got this? As we have seen in the three-phase induction motor, how the rotating magnetic field is produced. So when we give the three-phase AC supply to the stator winding, right, then the revolving magnetic field is formed, and that revolving magnetic field will cut the stationary rotor conductors, and then the rotor starts rotating. Now in the synchronous induction motor, the same construction is used, but here the rotor is what? Of wound rotor type, and it is a three-phase rotor winding, right? But here instead of giving a three-phase AC supply, here it is to be given as a direct current, right? So for the synchronous mode of operation in the synchronous induction motor, we have to give a direct current to the rotor winding. So when the direct current is given to the rotor winding, then the fixed poles are formed in the space, right? And due to the fixed poles, they will get magnetically locked with the rotating magnetic field developed by the three-phase stator winding carrying AC, and the motor runs at constant speed that is equal to the synchronous speed, right? So in this way, during the normal running operation, this motor will act as a synchronous motor, right? Now to understand the working properly, we must know the rotor connections for DC excitation. So the DC excitation to the rotor windings may be provided in a number of different ways as shown in figure. So the simplest ways to provide the excitation to the rotor winding are of two types, and that are the two lead and the three lead connections. So in the two lead, the winding is star connected and the two line terminals are used. So as shown in figure 1, right? That is figure A. The two line terminals are used and the third is isolated. In the figure B, the two line terminals are connected together putting their phase windings in parallel, right? And the parallel combination is connected in series with the third phase winding. So in the second method as shown in figure B, the MMF pattern is identical with that of a normal three-phase excitation at the instant that the current in one phase is at its peak value. So here the connection shown in figure B is similar or identical with that of a normal three-phase excitation, right? Now, as can be seen from these diagrams, that the current distributions in this figure is unbalanced, and unbalanced secondary heating is avoidable with a three-phase secondary. But two-phase arrangement, as shown in figure E, equalizes the heating. Right? Now see the figure E. Here the unbalanced heating is there. Why? Because only the two windings are used. So here, due to the current distributions, right, unbalanced secondary heating is unavoidable with a three-phase secondary, right? But a two-phase arrangement, as shown in figure E, that will equalizes the heating. However, there is no closed secondary loop apart from that through the exciter, so that the damping is not as good as in figure E, right? So those two phase arrangements shown in figure E and D give uniform heating but develop rather large harmonics and noise. So reduction in exciting current can be achieved by use of multi-turn secondary, but consequently the induced secondary EMF at standstill is high, causing insulation problems. So from this we can understand, we understood that the unbalanced secondary heating is unavoidable with a three-phase secondary, but with a two-phase arrangement the heating can be equalized, right? So, and that is shown in figure E. Now the rest of the connection shows that there are three windings and that are connected in series or in parallel, right? And the heating is unavoidable. But using only two windings, the heating can be equalized, right? But the induced secondary EMF at standstill is high, and that causes the insulation problem. So for an ordinary induction motor, the value of magnetizing current is kept as small as possible. Why? To ensure a good power factor, right? That for an ordinary induction motor, the value of magnetizing current is kept as small as possible to ensure a good power factor. So there is a relation between the power factor and magnetizing current. So very short air gap such as expected in plain induction motor would result in a very heavy armature reaction when operating as a synchronous motor, because the total field ampere turns would be reduced for a given number of armature ampere turns. So the actual fact is that a synchronous motor needs a heavy excitation to enable it to operate on a leading power factor. The relatively larger air gap, though, results in a low power factor when operating as an induction motor, but at normal speed, this is immaterial since the power factor can be controlled by variation in DC excitation. Right? So when it can be improved, when it will act as a synchronous motor. So the larger air gap and the increasing excitation EMF per synchronous impedance results in a higher peak synchronous torque. So the synchronous induction motor is provided with a large air gap as provided in a plain induction motor. So this is the answer for the question that in why a very large air gap is provided in a synchronous induction motor. So what is the reason for that? If a very short air gap is there as that of the plain induction motor, then it will result in a very heavy armature reaction when operating as a synchronous motor, because the total field ampere turns would be reduced for a given number of armature ampere turns. Right? So the relatively larger air gap is necessary in a low power factor when operating as an induction motor. That's why at normal speed this is immaterial. This is not so important that the air gap is large, since the power factor can be controlled by variation in DC excitation. Right? Means what? When the motor is acting as a synchronous motor during normal working condition. So the larger air gap results in a high peak synchronous torque. So the synchronous induction motor is provided with large air gap as provided in a plain synchronous motor. So a long air gap gives a stiffer machine with large overload capacity. So there is a direct relationship between overload capacity and air gap. The rotor slots are made fewer, means less in number, and larger in size. So these machines are provided with heavy rotor winding in order to have a low starting current and slip, which facilitates in pulling it into synchronism. So also in order that induced EMF in the field at starting may not be too high. The field turns provided are few in number and the excitation voltage is kept low. So as the exciter winding serves the purpose of damper winding, so there is no need of providing separate damper winding with synchronous induction motor. As we know that in synchronous motor, damper winding is used for starting purpose to improve the starting torque. But here the exciter winding is used as a damper winding. That's why there is no need of providing separate damper winding with this synchronous induction motor. Now we'll see the typical circuits for synchronous induction motor. So first we'll see the schematic arrangement of starting a synchronous induction motor. So as shown in figure, the synchronous induction motor is started as a slip ring induction motor by inserting resistances in the rotor circuit through slip rings and TPDT switch. So when the additional resistances are completely cut out and the motor attains the normal induction motor speed, the rotor is disconnected from the starting resistances and connected to the exciter, which is usually mounted on the same shaft, and the motor will operate as a synchronous motor. Right? So got this. So first, the synchronous induction motor is started as a slip ring induction motor by inserting this starting resistances as a variable resistance connected in series with the rotor circuit through the slip rings and TPDT switch. Now when this whole resistance is cut out completely, then it is disconnected from the rotor circuit and the rotor circuit is connected to the exciter. Why? to operate the motor as a synchronous motor. Now the second typical circuit is that with a permanent exciter in series with one of the leads. Now the exciter can be left permanently in series with one of the leads as shown in figure. So provided the induced voltage at standstill is not too high. So what is the condition? That induced voltage at standstill should not be too high. So at the starting instant the exciter is unexcited, and when the starting resistances are cut out, the machine runs as a normal induction motor. After a short delay, the exciter voltage builds up and field current is caused to flow through one phase of the rotor winding to the start point when it divides between the other two phases in parallel, each of which carries half the exciter current, and the rotor MMF is almost sinusoidal distributed. As this field is established, the machine pulls into step and the machine operates as a synchronous motor. So it is same as to that of the previous typical circuit, but the difference is that here the exciter is permanently connected to one of the lead of the rotor circuit. So the procedure is same. First it has to be run as a slip-ring induction motor by inserting the variable external resistance, that is the starting resistance, connected in series with the rotor circuit by slip rings, right? And when the whole resistance is cut out, right, then by using the exciter, the motor can be operated as a synchronous motor. So with secondary rheostats for starting, such a motor gives low starting current and high starting torque of the wound rotor induction motor and an improved power factor under load, right? So due to the addition of this external resistance and exciter, the starting current is low and the starting torque is improved, and that's why the power factor is also improved under load condition. Hence the synchronous induction motor is essentially a motor having the induction motor features like high starting torque with low starting current, combined with the synchronous motor features like constant speed and power factor control. Means what, here the features of two machines are combined, that is for power factor improvement and constant speed it is acting as a synchronous motor, and for variable speed and low starting current at starting, right, and high starting torque, it will be acting as a induction motor, right? So the features of two machines are combined. So the interesting point about this motor is that its peak torque as an induction motor exceeds that as a synchronous motor. So if it is momentarily overloaded as a synchronous motor, it may continue to operate as an induction motor with considerable pulsations of current and torque due to DC until the load falls and it is able to resynchronize. So however, the extra cost, low efficiency as compared to that of the standard types, the small copper space available with a distributed rotor winding, and the necessary compromise between the excessive ring voltage at start or excessive rotor current in operation are severe handicaps, right? So there are some drawbacks or limitations of this motor, that is of extra cost and low efficiency as compared to that of the standard types of induction motor, and there is a small space for copper with a distributed rotor winding. That's why compromise has to be there between the excessive reading voltage at starting or excessive rotor current during the operation. So these are the limitations. Now we'll see the characteristics and applications of synchronous induction motor. A synchronous induction motor can also be made of silane pole type, combining the high efficiency and low excitation loss of the silane pole synchronous motor and the excellent starting characteristics of the induction motor. So in such motors, the DC field winding is of normal construction and an independent or three-phase starting winding connected to the slip rings is placed in slots in the pole shoes. So each winding can be designed almost independently to fulfill its own function with consequent improvement in synchronous running and exciter circuit conditions. So there are three important characteristic torques, that are starting torque in the induction mode, pull-in torque during the synchronizing, and that is synchronizing from the induction to the synchronous mode, and pull-out torque corresponding to the maximum torque in the synchronous mode. So there is naturally a close relation between the pull-out torque and the full load power factor. So a motor excited to operate at a power factor of 0.9 leading when developing full load torque might have a pull out torque 1.5 times of full load torque. But if it were designed for unity power factor operation while developing full load torque, the pull out torque and the necessary exciter rating would both be considerably reduced. The typical curves of stator current, reactive power and power factor against active power output for a machine excited to unity power factor on rated active power output are shown in the figures A, and in figure B it shows the same quantities for a motor with a strong excitation. So the strongly excited motor has a large overload capacity, but over the range of normal load its power factor is reduced and electrical loss is increased. So depending on this characteristic curve, the synchronous induction motor is rarely built for ratings below 25 kW because of the relatively higher cost of the exciter. Synchronous induction motors are used where a high starting torque and constant speed operation are required. So typical applications of synchronous induction motor include fans, pumps, blowers, generators, air compressors, ammonia compressors, machinery and line shafting in industrial work such as cement mills, rolling mills, flour mills, paper mills, rubber works and textile mills. The synchronous induction motors are very often installed along with other induction motors so that they may improve the overall power factor of the system. So their leading kVAR capacity is designed to offset the lagging kVAR demand from the induction motors. So they have been made for ratings as high as 30 watt, 30 meg. Now the second special purpose machine in this lecture is permanent magnet synchronous motor. So first we see the construction. A permanent magnet synchronous motor is constructed by embedding permanent magnets in the rotor as shown in the figure. So as shown in the figure, so there is a permanent magnet and that is embedded, right? And the rotor itself has a squirrel cage construction to provide starting torque. So the rotor is of squirrel cage type and the magnetic path through the annular core carrying the cage winding serves to protect the magnet, but it must be slotted to prevent flux from permanent magnet being short-circuited in normal operation. Right, so here the cage winding is there, that's why it is a squirrel cage type rotor, and then permanent magnets are embedded, and then the slots are there, and that are the reluctance slot. Then the upper portion is the stator winding. Now working. The rotating stator field may be obtained by means of any one of the winding configuration previously discussed, that is, by using the shaded pole or permanent magnet or permanent capacitor construction, right? So now the permanent capacitor construction, that is capacity 1, so provides a two-phase stator near full load, and therefore uniform rotating stator field is developed and is commonly employed. So when the motor is connected to a single phase AC supply, it starts as induction motor. attains nearly synchronous speed and locks into synchronism with the rotating stator. With the rotating stator field near synchronous speed, and that's why it operates as a synchronous motor. Now the application. So such a motor is quieter in operation and has high power factor and efficiency approaching that of a polyphase motor. So it is thus finding more use even in the low integral kilowatt ratings. So this is the permanent magnet synchronous motor, and that is very simple. The difference is that here only the permanent magnets are embedded in the rotor, right, and the slots are there for having a low reluctance path. That's why they are known as reluctance slot. Thank you.